Hello, I'm Junyoung Kim, PhD student in KIST lab. Today I'm going to talk about the paper named Temperature-Dependent Plasmonic Response of Graphene Nanoresonators, which published in ACS Photonics in 2022. Then let's go into today's presentation. Mid-infrared plays a crucial role across various fields. In communication, the mid-infrared is suitable for free-space optical communication due to its minimal atmospheric absorption, so that it enables high-speed data transmission. This makes it a promising technology for next-generation communication systems. In the field of spectroscopy and sensing, mid-infrared is where molecular vibrational modes are most pronounced, allowing it to detect spectral fingerprints of specific substances. This makes it invaluable for chemical analysis, gas detection, environmental monitoring, and various industrial applications. In thermal applications, objects emitting thermal radiation below 1000 degrees Celsius emit the mid-infrared range. This characteristic is critical for technologies such as radiative cooling, thermal radiation control, and energy harvesting. All of them play vital roles in modern energy management systems. Given these broad applications, our lab focuses on exploring the plasmonic properties in the mid-infrared range. Despite the potential of the mid-infrared range, the lack of efficient light sources, detectors, and materials remains a major limitation in mid-infrared research. Conventional bulk materials suffer from high absorption losses and poor light-material interaction in the mid-infrared range, as well as challenges in miniaturization and integration. One material has emerged as a solution to these issues: graphene. Graphene has exceptional electrical and optical properties with tunable optical conductivity over a wide spectral range. Through plasma resonance, graphene enables strong light-matter interaction in the mid-infrared range. Particularly, its dynamic tunability in conductivity and potential for integration with other materials make it an attractive candidate for coupling with optically active materials, unlocking new functionalities and applications in the mid-infrared range. Therefore, graphene has been widely used as an active device material platform for nanophotonic application. The first is the modulator. Graphene-based metasurface can be designed to modulate the amplitude and phase of reflection, transmission, and absorption to steering incoming beams or realize lens effect. Unlike passive devices, which cannot be modulated the device characteristic once the structure is determined, active devices using graphene can modulate the resonance of the meta-atom by modulating the Fermi energy of graphene. Next, we focused on molecular sensors. The mid-infrared range is where molecular vibration spectra are most pronounced, so that by matching the resonance frequency of graphene with the molecular vibrational mode, anti-crossing occurs, so it allows the sensing of molecules with that specific bond. By tuning the resonance frequency of graphene, broad range can be covered using a single devices. The third one is photodetectors. Graphene has high carrier mobility, which allows for a high-speed response and the ability to detect a wide spectral range. So it can be applicable for a broad range from visible to mid-infrared. Last one is using graphene as surface plasmon polaritons. SPP is a phenomenon where surface plasmon couple with photons in free space, and graphene is an ideal material for supporting SPP in the mid-infrared region. This paper, published in Nature Communications in 2021, was the first to image the acoustic plasma mode in a graphene dielectric metal structure. It resulted from the coupling of graphene plasmons with the mirror image in the metal reflective layer below, and the use of sub-nanometer thick dielectric allowed for very high electric field confinement. Like above, despite the growing interest in graphene plasmon, most research has been performed at room temperature, and the temperature dependence of graphene plasmon properties has not been widely investigated so far. While there has been little research on the cryogenic temperature characteristics of graphene plasmons, the paper published by the Basel group in Nature, they emit graphene plasmon using near-field scanning optical microscope. They observed that as the temperature decreases, the propagation length increases, which was demonstrated in the interference fringe patterns. The study quantified the dynamics of the quasi-particles that underpin the plasmon propagation. However, in this study, we aim to investigate the behavior of graphene plasmons as a function of temperature in a more conventional setup by performing far-field measurement with the HBN encapsulation layer removed, which allows us to study the temperature dependence dynamics in a simplified system. However, it's not possible to observe graphene plasmons in the far field using unpatterned graphene. When we illuminate the light into unpatterned graphene, we can get very low coupling efficiency. So that to overcome this limitation, graphene is patterned into periodic nanoresonators to enhance the coupling efficiency. Then the fabric pair modes of plasmons are bounded in graphene nanoresonators. With some assumption, we can achieve this simple dispersion relation of graphene plasmon. First, to investigate the temperature dependence of carrier concentration and the mobility of graphene, we measure the DC electric properties of graphene while varying its temperature from 300 to 100 Kelvin using a nitrogen purge cooling stage. The charge neutrality point drifts from 62 volt at 300 Kelvin to 76.5 volt at 100 Kelvin. The shift of CMP is 14.5 volt, correspond to the additional hole doping of 1.04 times 10 to the 12. Also, the increased hole doping of graphene is observed by blue shift of G and 2D Raman peaks. In addition to the change of doping concentration, the cooling also reduces the carrier scattering in graphene. In our measurement, there appears a monotonic increase of mobility with decreasing temperature. This feature can be described using three different scattering mechanisms: impurities, silicon dioxide polar optical phonons, and the longitudinal acoustic phonon in graphene. According to the past research, impurity scattering shows little temperature dependence. On the other hand, phonon-mediated scattering rates rapidly decrease with cooling. The mobility measured in our experiment shows a near-linear dependence on temperature, which agrees well with the previously reported measurement at high doping concentration. Then let's move on to the optical characteristic of graphene nanoresonators. We can see multiple resonance peaks in the normalized extinction spectra. The left peaks are due to hybridization between graphene plasmons and surface phonon modes of silica. Such hybridized mode is called surface plasmon phonon polariton. Top two figures illustrate how the normalized extinction spectra depends on the resonator width and carrier density. Both peaks blue shift as width decreases and carrier density increases. SPPP peak intensity tends to increase with increasing the doping level unless resonance frequency approaches to the loss line. Unlike to the SPP profile, GP resonance becomes spectrally broader as the resonator gets narrower. It is likely due to fabrication imperfections such as edge roughnesses or resonator width variation within the array. Lastly, the most important point here, the temperature dependency. We can see that decreasing temperature leads to a slight blue shift and larger intensity of all extinction peaks. This trend can be explained by the increased carrier density and mobility in graphene and well matches to the electrical measurement. To independently estimate the doping level variation associated with cooling, we fit the measured peak position to the theoretical dispersion relation. You can see that resonance frequency measured at gate bias of minus 115 volt and minus 45 volt with both 300 and 100 Kelvin agree well with the resulting dispersion curve. I summarized the resulting carrier concentration at below table and figure. The estimated doping levels well match to the linear fit with a certain 300 nanometer oxide capacitance model. The amount of the additional hole doping is about 1.37 times 10 to the 12 inverse centimeter square. We speculate that the additional hole doping could originate from the releasing of trapped charges at the graphene silicon dioxide interface because this cooling-induced doping didn't appear when the graphene sheet was encapsulated by hexagonal boron nitride. To analyze the temperature-dependent characteristics of graphene plasmon at different widths and carrier density, I normalize each data using 100 Kelvin data. Because SPPP is highly affected to the substrate photon, let's focus on graphene plasmon only. In most cases, peak intensities increase with decreasing temperature. The peak intensity enhancement associated with cooling range up to 76%, and its dependency becomes stronger when the gate bias gets smaller. When the cooling-induced doping amount is same at any voltage, tendency becomes more significant because it has small amount of electrostatic carrier concentration itself. Then let's see the width dependency. In order to isolate the additional doping effect, I compare the result at different width sample at high gate bias. That means the effect of temperature-induced doping becomes minimized. It can be seen that the temperature dependency gets stronger as the width of the resonators get wider. That means wider one shows the large change in normalized intensity with temperature change. In this regime, the peak intensity variation is expected to mainly depend on the plasmon scattering rate. There are intrinsic and extrinsic factors that affect the damping of plasmonic response of graphene resonators. Such as impurities and dielectric phonon, intrinsic losses are introduced to explain how graphene plasmon works depends on temperature. However, extrinsic losses are independent to the temperature, which induced by geometrical irregularity. Fabrication imperfection like edge effect or proximity effect hence produce irregular unicell periodicities. However, these fabrication constraints impact the broadening of the resonance, whereas the intrinsic losses are mainly temperature-dependent factors. The important point here is that, assuming that the same amount of fabrication imperfection occurs regardless of the resonator width, a sample with a narrow resonator width has a large width variation. Then, the same manner here, narrower one has a larger contribution to the temperature-independent extrinsic scattering rate. So, wider nanoresonator sample has stronger temperature dependency than those in narrow one. Finally, to exclude the effect of cooling-induced additional doping, we carefully equalize the resonance frequency at every temperature. That means we can isolate both additional doping effect and plasmon damping variation. Even after excluding the additional p-doping effect, the normalized peak intensity still increases with cooling. Also, the line width of the GP resonance peak, which is inversely proportional to the plasmon relaxation time, is observed to also decrease with cooling. Interestingly, the temperature dependencies of both normalized intensity and line width of GP peak show a similar trend independent of doping level. We attribute this remnant increase in peak intensity and decrease in peak line width to the reduced damping of graphene plasmons. As temperature drops, the phonon-mediated carrier scattering mechanisms are suppressed. Thus, the plasmon lifetime is expected to be prolonged. It leads to a stronger resonance and increased quality factors. To conclude, we have analyzed the temperature-dependent plasmonic responses of graphene nanoresonators on a silicon dioxide substrate in the far field. When the temperature drops, temperature dependency gets stronger when the gate voltage is smaller and resonator width is wider. The increase in graphene plasmon peak intensity can be attributed to the cooling-induced additional p-doping and suppression of phonon-mediated scattering mechanisms at low temperatures. Thanks for listening, and this is the end of my presentation.